I just welcome everyone to our last pair of keynotes. I'm David Lazar, and I'm extremely pleased to be here. It's been a wonderful first day of IC2S2. So again, thank you very much to the organizers. And my job here is to introduce the final two wonderful keynoters. And I'll first introduce Brandon Stewart, who's coming to us from the Wild West of New Jersey, associate professor of sociology at Princeton, a star in natural language research, and PhD in government from Harvard and back in a decade ago, and author, or one of the authors of the very influential book Text as Data with Justin Grimmer and Molly Roberts, and currently serves as co-editor-in-chief of Political Analysis and associate editor at Sociological Methods and Research, and recipient of many wonderful and much-deserved early career awards. So we are extremely fortunate to have Brandon joining us. So with that, give Brandon a hand.
All right. Thank you very much for the generous introduction, and thank you so much to the organizers for both the enormous work that I know goes on in putting on these conferences, but also for the invitation, which I greatly appreciate. So I'm going to talk to you today about this project about design-based supervised learning. And I'm going to start with a little bit of a story. So I want you to imagine, as will be easy for many of you, that you are a social scientist. And particularly that you want to study something. Like, for example, Erica Franklin Fowler and her co-authors wanted to study the effect of political advertising online and offline. So they wanted to compare, do the kinds of ads that appear on Facebook tend to be more attack ad-like than the kinds of ads that appear on television, right? These are the sorts of questions they're asking. And so in order to do that, they needed to go through ads, like quite a lot of ads, and annotate the type of ad that they were. Are they an attack ad, a promotion ad, or a contrast ad? And so they were sort of, you can imagine them, you can imagine yourself facing down this difficult question, how am I going to get all these things annotated? And then you start reading the literature, and you see things like, well, ChatGPT outperforms crowd workers for text annotation tasks, or large language models might transform social science. And you think, okay, this is like a real possibility. And in fact, if you get even to the more recent stuff, we might see evidence that LLMs outperform expert coders. And you think, yes, okay, I'm going to try this. And so you go to your favorite large language model and you put in a prompt situation like this. So you ask it some question, in your judgment, is the primary purpose of the ad text to promote a specific candidate, attack a candidate, or contrast the candidates, and then you give it the text of the ad. And all large language models, right, are going to roughly have this kind of form. There's some code book that says what it is that you would like to come out. There's the thing that you would like annotated. And then sometimes, particularly in the older LLMs, you kind of need to prompt it to give you an answer. And then it gives you an answer. And you think, yeah, this is great. This is pretty accurate. And maybe you even try and go in and you do something slightly more complicated, which you do the kind of few-shot learning variation where you give it a couple of examples, and maybe that makes it even more accurate. But the problem is you don't know how accurate, because, of course, you haven't actually labeled a bunch of documents. And so you have to take a guess, like, is this going to be accurate enough for my study? And so at that point, again, you might consult the literature, and you might, for example, draw on some work by Etienne Olien and update the data from that article to figure out, well, how well has LLMs done across all of these different applications that have been published in the social sciences? And you would get a histogram that looks like this, and you would sort of see there's actually a wide variation in the F1 score, a measure of accuracy, that these LLMs have performed. And so now you're in a bit of a bind, right? You're sort of asking yourself, well, is it going to be accurate enough for my case? And so you go through and you code a bunch of things by hand, and you check the LLMs, and you see, yeah, This is actual data from the Fowler case, performance for zero shot and few shot, those two strategies across a few different LLMs. One of the fun things about LLM talks is that they're like looking at these plots as like carbon dating the paper really precisely. Like you can see what models people used and you're like, yeah, I know what month that paper was written in. But this is, these were run about a year ago, excuse me, but we've done this with all the newer models, and you get basically the same thing. In fact, it's basically at that point, right? It's that same spike that was found in Etienne's work and in our own sort of literature survey. And so the question is this accurate enough for you to do science that you believe in? And so what you might do at that point, and I promise I'm nearing the end of this opening story, what you might do at that point is you might go in and say, okay, I'm going to run a simulation where I simulate what would happen to the regression that I care about if I have accuracy that looks like this. And that's when you get results like this, and maybe your heart drops a bit. Okay? Because what you're seeing here along the x-axis is a measure of accuracy, and you're seeing three things we might care about: bias, coverage of a 95% confidence interval, and root mean square error. And what you're seeing here is when you have F1 scores of the kind that we were looking at just a second ago, between 0.7 and 0.8, the coverage can be incredibly, incredibly low because the bias is quite high. So this is a methodological problem that's going to face social scientists trying to use LLMs, and that is that it's not just that the LLMs make mistakes, it's that they make non-random mistakes, and that those non-random mistakes will turn into biases in the downstream regressions that we might be trying to run using our LLM annotations. And that's because these errors are correlated, right? They're correlated with observed and unobserved variables in the downstream analysis that we ultimately care about. And ignoring those prediction errors, as I said, is going to produce large bias, but it's also going to produce standard errors that are way too small. We're going to be really overconfident, right? Which is not at all what we want in our analyses. And this can happen even when the prediction accuracy is really high. I myself have written papers where we have a strategy for doing text as data. We see that the accuracy is like pretty high, and we're like, hey, it's really high. That's probably good enough. But actually, that doesn't protect you from these sort of extreme biases. And in fact, you can see that you can have cases where you can have F1 score above 0.9, something that I think most people would be very excited about to see in their measure, and still have 95% confidence intervals that don't crest 50% coverage. So I'm going to propose a strategy to deal with this called design-based supervised learning. And it's a general framework for using predicted text or image or audio or any kind of predicted label for downstream analysis, but without bias. And it's going to work by combining the predictions that you get out of the LLM with human expert-driven labels using a doubly robust procedure. And the core assumption that's going to make this work is that users, that you, the researcher, can control how to choose which documents are going to get expert coded. So as long as you have that, you can guarantee this assumption holds by design, which is why we call it design-based supervised learning. So importantly, this means there's no assumption about the prediction errors, there's no assumption about the model classes, anything like that. And the properties you're going to get are consistent and valid confidence intervals, even if the predicted text from the LLMs or other methods are arbitrarily biased. Sorry, the little thing's falling off my ear. We're also going to reduce mean square error when the prediction accuracy increases. So as LLMs get more and more accurate, their prediction accuracy is going to go up, and that's going to mean you're just going to get more and more confident in the results of your data analysis procedure. But you're always going to know the coverage is going to be right. It's just that the confidence intervals are going to get smaller and smaller. So in short, what we're arguing is that DSL exploits the power of LLMs without introducing bias. So short outline for the rest of the talk. I'm going to give you some intuition and a little bit of the math of design-based supervised learning. And particularly, I'm going to try to convince you that it's the thing, in simple cases, it's the thing you probably would have done if I had set you in a room and made you solve this problem. There's a sense in which it pops out really straightforward, elegant solutions. I'm going to give you an empirical validation of DSL, both done by our group as well as by an external group. I'm going to talk briefly about extensions and future plans for the work. And finally, I'm going to take a few minutes at the very end of the talk to just say generally how I think social scientists can productively engage with LLM work, or at least the way that I tend to think about it in structuring my own research. Okay, so I'm going to be drawing on a number of different papers for this talk, particularly these first two. This is work done with Naoki Egami, one of my former students who is now a tenured professor at MIT, Hanying Wei, who's his student, and Musashi Hinck, who was my postdoc and now a research scientist at Intel. Okay. So the first thing I want to tell you before even giving you specifics of the solution is just that this is not something that we created out of whole cloth. This draws on a long literature of semi-parametric inference and double machine learning that goes back to this sort of foundational work by Jamie Robbins and Andrea Rodnitsky in the mid-90s. And there's also been a lot of work trying to address this question of when I have a predicted variable, whether or not that's from text annotation, from satellite imaging, from web scraping data, from anything, right? What do I do with it? And there's been a number of papers like this in recent years that have attempted to solve this problem, particularly using various kinds of parametric assumptions. Now, in the last maybe 2 years or so, there has been a set of methods developed that are very closely related. So there's our work on DSL that I'm going to tell you about today. There's the work on prediction-powered inference that is a fantastic line of work that was developed at about the same time as ours and is sort of has similar estimators, but that are derived from a kind of different statistical tradition. And I'm happy to talk about that in the Q&A if people are interested. And model-assisted impact analysis, which is another piece in this sort of broader way of doing this with semi-parametric inference. And this is going to make 3 key contributions. So we're going to cover any case where the thing that you are trying to label with the LLM is either the outcome in some kind of regression or an independent variable in some kind of regression or a combination. We're going to provide a data-driven power analysis so that once you've collected some data, how much more you need to collect in order to get the standard errors to where you want them to be. And we're going to produce DSL estimators for a wide variety of methods and models and release them in open source software. Okay, so let's talk through the assumptions of how this works. We're going to introduce a little bit of notation. We're going to have Y is our outcome of interest. That's like in the story I was telling you, the tone of the political ad. And this is something that we imagine is costly to measure, but is doable with experts, right? Maybe it takes a panel of experts looking at it to come to the right conclusion, but we're going to assume there is some mechanism through high cost to get the true label out of the world. Then you have Q, which is a set of LLM surrogates, and X, which are the other variables that are in your regression. So in the context of the political ads, Q is the predictions that the LLMs made for us, and X is things like the candidate, the party, and whether or not the ad was posted on television or on Facebook. So the key thing that our assumptions are going to revolve around is this quantity R. That's a sampling indicator that says R is equal to 1. When that happens, we get to observe the right label, right? That's the case where we paid the experts to go carefully annotate, or we annotated ourselves, and R equals 0 otherwise. And the core assumption that we're going to make, the design-based sampling assumption, is basically to say that that probability of expert labeling the document is known. And it can depend on the surrogates from the LLM. It can depend on arbitrary sets of covariates, but we just have to know it, and it has to be above 0. There has to be some chance of actually sampling those documents. Okay, so this is going to work when researchers have a population of documents and can control which documents they want to have labeled. And it's violated in settings where we need to say predict labels for future documents that don't yet exist, or when users don't control which documents are labeled. Okay, so our approach. So I'm going to show you the approach from the very first paper that we had, which is using bias-corrected pseudo-outcomes. And basically what's going to happen is we're going to replace the y's in our data set with this thing y tilde. And then that's going to let us run whatever analysis we wanted to run. So y tilde is going to be composed of two parts. There's going to be a part that is the prediction that we are making, and there's going to be this bias correction term that's going to stand in for all the cases all the cases that we didn't get to observe the true label. And the algorithm is going to be very simple. We're going to sort of fit a machine learning algorithm to learn how to make these predictions as effectively as possible. We're going to make those predictions. We're going to do the bias correction to form this y tilde term. And then we're going to run whatever model, whatever GLM model we wanted to run with that as our outcome. So this is going to turn out to be that we can prove under the setting where we know the design sampling weights, we're going to be able to prove that the coefficients we get with this DSL estimator are consistent and asymptotically normal. And what that means, right, in a practical sense, is that it's going to get you confidence intervals that have the correct properties. And this is, again, going to be true even if the LLM surrogates are biased or even if the underlying ML model is biased. It's going to be true under very limited assumptions because we get to control which documents get expert labeled. And so DSL is then going to reduce that root mean square error even more when the LLM surrogates are more predictive. So we can go back to that original simulation. This is up top, the simulation I showed you at the very beginning. And we can see that when DSL is applied to run these regressions, we get essentially zero bias. We get perfect 95% coverage. And as the accuracy of our surrogate gets higher, the root mean square error goes down, 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 which is good. Okay, so I promised I would walk you through a simple example to kind of try to show you that this model produces something that I think is very intuitive as a correction. And so I want to start by looking at what that nasty formula on the previous slide looks like when what we're trying to do is just calculate the mean, right? We just want to know what fraction of these documents are attack ads. Okay, so the way it's going to work is there's a predicted outcome, and then there's this bias correction term. And when we've done simple random sampling of the documents, you get this simplification. So you get the average of all the predicted outcomes. That is, you ask the LLM which ones are attack ads, and then you just average all of its guesses, right? So that gives you, okay, what fraction does the LLM think? Then what you're going to do over here is in the subset where you observe the expert data only, you're going to say, well, how much was the LLM off by? So this is the average of the LLM guesses, and this is the average of your experts. In other words, you're taking that small sample that you have, and you're saying, okay, what's the bias there? Okay, let's just scale it up and pretend that that's the bias for the whole set. So it's a very simple process of estimating the bias and then debiasing. And we can get some more intuition for how this works then by looking at what the variance of this estimator is. This is an approximation. The full derivation of the variance is in the paper, but it gives you an intuition for what's going on. There's two pieces. There's the variance in the unlabeled data of the predictions, and there's the variance of the errors in the expert data set. And because the number of unlabeled documents is huge relative to the number of labeled documents, right? We might label 500 with our experts, but we might be working with like 20 million documents or something like that. Then this second term is going to be really, really tiny, right? Because that capital N, all the unlabeled things is going to be enormous. So that term's going to get very small. So we know that the variance is going to largely be determined by this first term. The second thing that we can see from this term is that as we do more expert annotations, the variance will go down. So if we want to get more confident, we can just, go and label more ourselves. We also know that when y hat is really accurate, the variance of the errors it makes is going to be small. And you can compare this to the variance of what just using your expert data would be and ignoring the LLM entirely, which would be the variance of y over n. And so you can kind of see how this is really going to work when the thing is accurate, because then the variance of the errors it makes is going to be a lot smaller than the variance of the raw variable. Okay, so we extend this to a much more general case. I'm not going to belabor this point. I'll just sort of put it up briefly for Statsy people in the room that might be interested. But basically, you can do this where the LLM is annotating any independent or dependent variable by framing the regression as a moment estimator. And then you directly debias the moment in a formula that looks a lot like the one that we had before. And this is going to allow us to generalize to a really broad class of methods. And again, we're going to be able to prove all the same things. When that sampling probability is known, we're going to be able to show this is asymptotically normal and consistent. So just some important details I'm glossing over, and you can check out the paper for more. We cross-fit a sort of generic predictive model between the expert coding and the surrogates and covariates. What that means is that you don't have to do this with just one LLM. You can have many different LLMs. You can have a whole group of LLMs all making predictions, and you can pull them all together in this framework. It also means that we can sample expert-coded documents conditional on the surrogates or other data. So this turns out to be really important when the property that you care about is very rare. So you imagine we were in a beautiful world that does not exist where attack ads were exceedingly rare, right? They showed up in 1% of ads. Well, we could take our LLM guesses, we could find the ones it thinks are attack ads, and we could oversample on that. And this would still be fine, and all our nice properties would go through. The other thing that's really nice is you can show that the expert annotations don't actually have to be perfect. They can have completely random errors, and it is OK. But obviously, we want our experts to be as accurate as possible. OK, so let me show you an empirical validation. This is the Fowler study. They have 13,000 expert-coded political ads. They're doing a downstream analysis that is a regression of the tone of the ad on whether or not it's posted on Facebook, plus a bunch of candidate fixed effects. And what we're going to do is we're going to just pretend like we have 1,000 documents that have been expert coded, but all the rest are uncoded. And we're going to see how well do we do relative to the full hand coding strategy by using the 1,000 and the LLM. Okay, and what you get is something like this. So over here is the benchmark estimate. So the benchmark estimate is like the oracle. It is the thing as though we had all 13,000 documents. So that confidence interval there, anything shorter than that is a lie, right? Because that is the case where we observe the full data. And so speaking of lies, we move over here to classical supervised machine learning. This is just fitting one of those classic ML models to predict the label and then using the predictions as though it was true. And you see you get these very tight, way too tight confidence intervals that are all over the place. LLM estimation is similarly going to bounce around a lot, but DSL is going to be centered essentially exactly on the truth with confidence intervals that are a little bit wider than the dashed gray lines that indicate the oracle, but that is as it should be because we know less than if we knew the right labels for all 13,000 documents. And you see that the coverage that we expect to get based on our statistical theory does in fact hold, that kind of regardless of the LLM you use, you get 95% coverage across the board. So one of the nice things is that you can frame this in terms of the gains of how much more what would be the equivalent number of hand-coded documents to get the same standard errors? And what we find is that doing this again, depends on the accuracy. So one of the nice things here is the F1 score for these three categories, promote, attack, and contrast, is quite different. And you can see for the cases where the F1 score is very high, this is like having 50% more hand-coded documents. which is really nice. So it's basically a way of sort of powering up our inference using generative AI. We can do this for a different case. So this is work by Pan and Chen. This is a case where the text is the independent variable. And again, we can see that the classical supervised models are sort of all over the place. Here, the confidence intervals are way too big. And that's because the unknown thing is now in the independent variable. LLMs are still all over the place. And DSL is getting you the sort of perfect coverage that you would like to have. Now, I promised you that I would also show you briefly benchmarking from another group. I feel like the most compelling evidence that a thing works is when somebody else tries it and puts it to the test. So this is a great archive paper that recently came out benchmarking DSL and PPI and sort of comparing them on some different data generating processes. What you find here is along the x-axis, you have the number of unlabeled samples. And up at the top, you have the number of gold standard samples. And here we have RMSE. And the lower RMSE is better, right? We want lower error. The blue is the gold standard only estimator. It's as though we only had that expert data. So, the line is essentially flat. PPI is this green line. It's doing a lot better than the blue line. You're getting some real efficiency gains. And then we're down here at DSL in the orange line, and we're getting even more gains than that. I should say PPI is a fantastic framework. I love it. Honestly, I care a great deal more that you guys do this kind of debiasing in your own work when you're using LLMs than whether or not you choose their thing or our thing. That's like not the point here. The point is they both work. And so you should really consider them in your own work. Another piece that we add is power analysis. So when you start with a certain number of gold standard labels, we can predict for you what the standard error would be if you collected more gold standard labels, which can be really nice as a mechanism for sort of trying to assess whether or not it's essentially worth the extra effort to do that labeling. Some other current and planned extensions. One of the things that we do, building on previous work from the PPI authors, is introduce a technique called power tuning, which allows you to guarantee that you have smaller asymptotic variance than the expert annotations alone. This is really great because it means that as long as you're willing to use the LLM to do the annotations, which is a easier and easier thing to do every day, this procedure can't hurt you. Right? It does not matter how bad the LLM does. Asymptotically, it's not going to hurt you. We have a number of models in the current software that's available at dsl.software, and I'll throw that link up at the end. But we have OLS, we have Logit, we have fixed effects. We've also implemented Poisson. I think we haven't pushed it yet, but it's coming. And we're currently planning an extension where we add all generalized additive models. And so that means any hierarchical model, any kind of spline-based model, all of those things you'll be able to do as well. So if there's some kind of class of model that you think you might want to do with LLMs, and it's not in this set, come find me during the conference and tell me about it, because we really want to make sure that this is getting everything that everyone could possibly need. You'll see me around. I'm the one in the straw hat. I'm very easy to spot as a result. Okay. So concluding remarks on DSL, and then I want to talk about how I think about LLMs in research more broadly. LLMs obviously have huge potential for large-scale annotation. We've seen many papers at the conference, and I'm sure we'll see many more tomorrow about this. As with other prediction methods, LLMs have non-random prediction errors, and ignoring those prediction errors comes with significant peril. But DSL has a nice general framework to use those predicted text labels for downstream analysis. And so there are ways of getting the benefits of the LLM without paying those costs. Okay, the package, if you want to do this, we have an R package called DSL available at dsl.software. And so again, if there's something that you would like to see, we're going to push out a major new update in the next few months as we build in all the GAM stuff. And so definitely let me know if there's something else that you would want to include. And I will say, if you're more of a Python person, we're working on a Python package. We don't have one yet. Luckily for you, PPI has a Python package. So you can also do PPI if you... so you have no excuse, no matter your programming language, for not trying to do this stuff. OK. So let me talk very briefly here at the end about the way that I think about how social scientists can use LLMs. And I think about there being 3 branches of research. So the first is interrogating LLMs, thinking about their capabilities, how they work, how they'll shape our world. I think this is something that social scientists and computational social scientists more broadly, include all of our friends in computer science who do computational social science. This is the kind of thing that we're really well trained for. And so I think there's a lot that we can do here. The second is integration. That is taking the LLMs and using them to do tasks we were already doing. And then finally, there's innovating. There's using the sort of generative capability, in particular of LLMs, to conduct new kinds of analyses that weren't possible before. So I'm going to give you just some quick examples from these from my own research, just to sort of characterize what I mean. And I want to emphasize that these are all possible due to interdisciplinary collaborations, right? This is the kind of work interdisciplinarity is great for. So in the first couple of months after ChatGPT came out, so basically January after it came out in like November 30th, my postdoc Dennis Peskoff and I wrote this paper that came out at ACL that year, thinking about how ChatGPT could be used for information retrieval and search. And particularly thinking about, we had a bunch of different experts from wildly different fields, from quantum information to family medicine to opera, ask questions that they commonly get asked, as well as more niche questions. We produced responses for them, and then we had them evaluate them. And what we found is that the results were rated as highly credible, but they weren't always particularly accurate. And they essentially, at that time, never produced source material that you could use to go check it. More recently, though, I think there's other interesting questions. So this is work with my former student, Hanying Wei, who just presented it in this room. I was kind of hoping to be able to direct you to her presentation, but the ordering got away from me. But this is about questions about how sensitive LLMs are to propaganda and what happens when propaganda gets into the training data of LLMs. And again, these are questions that I think social scientists are particularly well suited to ask, because it opens up these kind of deeper questions about, well, what kind of socio-political contestation is there going to be over the nature of training data in the future? Integration is first like the kind of task that I talked about already. So the DSL work is an example of integration, building statistical theory around these tools. Another good example of integration is we have some work that Greg Lancelotti, who's here at the conference and you might see around, and I and a number of other collaborators have on using police body-worn camera footage to study use of force. And here's an example where you have this incredibly rich information, all of this body-worn camera, just terabytes and terabytes of it deleted every day. We can use AI to help make sense of it and try to understand the accuracy of administrative policing records. And then finally, we can think about innovation. So we can ask whether or not we can do different kinds of tasks than we can do before. This is a figure from some work by my graduate student Till Singer and colleagues on a technique we call auto-persuade, which is a way of iteratively refining more and more persuasive arguments by a sort of interface between surveys and LLMs. And again, that sort of capacity to kind of generate new messages is something that I think is, genuinely new. And I think we've only barely scratched the surface of the kinds of new things that we can do. So anyway, this is the way I tend to think about these things: interrogating, integrating, and innovating. And hopefully, this will inspire you to do some of those things of your own. And that's what I've got for you. So thank you very much. More information about me here and software here.
Terrific. So we have time for questions and answers. I will do the pointing and you'll do the answering.
I would love that.
Hands up for questions. I guess we'll begin in the middle there.
So I love that you can oversample rare things. That was going to be my question.
Yeah.
My new question is, what about more elaborate sampling procedures? If I did it, is it okay? Or do I need to have done it in one of like 7 ways for it to be okay?
Excellent. Okay. So basically, you have to be able to write down the sampling weights. So the thing that we don't know how to do at the moment is like a real active learning kind of setup where, you check the answers and you run the regression and then you resample optimally based on those previous samples. I think that could be done. I think, to be completely honest with you, our feeling has been this is likely to be very tedious for very little gain, and tedious for us, not tedious for the user, but still. And so what we have found is that it is hard to do much better than stratifying on our guess of the outcome in the case of rare things. And in the case of relatively frequent things, it just doesn't matter that much. I will say that the PPI literature that has sort of evolved in parallel with this has also taken up some of this optimal sampling of observations approach. And so there may also be answers there. I think one of the good things about multiple people having this essential same idea at the same time is that you get some nice cross-pollination as things naturally arise in different settings.
Terrific. Just a few rows back. And we'll get the mic to you. So I'm trying to make it as difficult for our mic holders as possible to go into the.
Thank you, and thank you for a super, super nice talk. I mean, this will be very, very useful. Just can you explain why it's not a problem that we do not random sample when we want to do bias as the correction? This is to the rare event problem, right? If something is very rare, we have multiple covariates, and then the size that we would have to annotate using random sample will explode. So why is this not a problem when you want to bias correct?
Oh, yeah. So what I was saying, so you're totally right? If it's very rare, you have to sample randomly, you have to sample a ton. But you can sample conditional on basically anything. And so if your classifier is reasonably high recall but low precision, right? In the sense that maybe any given time it says this is an attack ad, it isn't, but it's pretty much getting all the attack ads, then if we just sample our expert coded set conditional on that prediction, then it'll be okay, because we'll basically oversample the true rare class by proxy. And so it's basically just another way of saying the rare outcomes isn't a huge problem if you have a decent proxy for the outcome that you can sample on. And it just turns out that by construction we do, because that's why we're doing DSL in the first place, is we have a prediction for the outcome class.
And then we'll go to the distant left over there. We have someone on that side. Great.
Brandon, amazing work, and good to see that some of these sort of simulations and checks are in there. One thing that I'm wondering, imagine that it's very expensive to create data and annotate it. So you have one team creating data, annotations, and you have thousands of teams using that data downstream. But it's so expensive to annotate, say it's in surveys, costs couple of $1 million to create that.
Yeah.
How do you think about the coordination of debiasing happening across studies where they use the same, say, labels over and over again to do the debiasing? So can you talk a little bit about that sort of correlation that happens now across different teams?
Yeah, I think this is a great question. So we're mostly, I'm mostly responding to the social science literature where everyone's sort of reinventing the wheel and creating their own measurement of a thing, and so this doesn't come up as much. But you do have these kind of big science things where there's a very expensive annotation that lots of people could share. So the problem is when you collect new data that people might want to then use, you no longer have randomly sampled from that new data, right? And so the question is, how does this expert data that came from somewhere else do at debiasing this new data? So it might be fine. In some formal sense, what this comes back to is a problem of if y'all are familiar, I know the question asker is, but more general, if you're familiar with the idea of propensity scores, right? You could imagine a situation in which we're estimating the propensity score. So we're going in and sort of and estimating, like, how does this gold standard data we have relate to this new data set that we've collected. That works, but you lose some of the beautiful guarantees that we have here. So the reason we can get such strong guarantees is because the propensity score is actually known. It doesn't have to be estimated. You could imagine, though, backing into a situation where we estimate the propensity score and we have to assume something slightly stronger, but it turns out that it's fine because this expert labeled data is close enough to the kinds of data we actually observe that it's okay. So anyway, that's just an off-the-cuff answer. I do think this question, this would be aided a lot by having a real, like, concrete big example. And so I think if you have something in mind, like, come find me, like, let's talk about it, because I think this is a really important problem.
And one more question here.
Thank you for your talk. So you motivated this with attack ads. And I could imagine that two experts disagree, whether it's an attack or not. And so how do you handle the fact that the ground truth is not purely objective?
Yeah, I think this is a great question. So I'll tell you how I handled it in this case. We handled it in this case by just assuming that the codes that Fowler et al. Gave us were correct. And so that's, in terms of mechanically, how does that work here? But how should you handle it is a different question. What I would say is that I think we have to commit to the idea that there is some truth, that there is some right answer, or we're just in a completely different scenario, right? So it might be that we're in the scenario where there is no right answer because what we're interested in is people's subjective opinions, right? If, for example, whether or not someone perceives it to be an attack ad is actually a really interesting thing aside from the question of whether or not a political science expert thinks it is. But at that point, we're doing a survey. And so we have to think really carefully about the distribution of the respondents, right? We can't just pick random people anymore. It has to be the right distribution of people. At that point, you could imagine, though, now if we had the right distribution, we could just use their answers. Because it turns out that even if it would be different expert to expert, we only need this to be right on average. And so if we think about the truth as like the limit of what every survey respondent would say, then any given one of them is a random draw from that distribution. We're okay. If we believe that there's like truly a right answer and it's just hard, I think that the first step is always revisiting the codebook. In my experience talking to people about Texas data stuff, the biggest thing is that people don't write down a codebook of what they think attack ads mean. And when you do that, you're forced to confront a lot of uncertainty and you have to go through it. But the other thing that you can imagine doing is doing some kind of team coding, having multiple experts. You could have some of the experts be like high-powered LLMs themselves. You could then adjudicate across cases where there's disagreement and call that the expert label. So we're pretty agnostic towards what the expert label is. The way we think about it is the expensive procedure that you wish you could do for everything. And then the surrogate is the cheap procedure that we do because we can't do the expensive procedure for everything.
All right. Approaching truth, I think, is what we'll end on. I want to give a last hand for our speaker. Thank you, Brandon.